Very good. Well, thank you for coming along, everybody. We got a really good group online here, and I'm really excited for our speaker this week, Tom Kralidis. Tom and I have been crossing paths since back when I was a Python programmer, which has been quite a while because I'm pretty much an R guy these days. Remember the OWS lib days when we were all trying to hack WMS and web processing services and stuff, and Tom was the guru that we could all go to for help with parsing XML with Lord knows what XML package we were using in Python those days. And times have changed. We've come a long way in open source web service development. The Python community's come a long way. The open source community's come a long way. And in the spirit of the ESIP IT&I Rants and Raves this year, this idea that we want to get back to the basics and kind of hear where things are coming from, some of the sources of why we're doing things the way they are now. I thought it'd be a really nice opportunity to have Tom come along and give us a little bit of a history lesson and a little bit of a status of where the open source geospatial community is in the Python world. So I've had a chance to flip through these slides, and I'm excited to hear what you got for us, Tom. So without further ado, I'll let you introduce yourself. Go ahead.
Okay, great. Thanks, Dave. Can folks hear me?
Yep.
Can folks see my presentation?
We can, yes.
Okay, cool. All right, thanks. So thank you to Dave for reaching out and allowing me this opportunity to present to you folks on the evolution of and some of the current state of affairs with regards to open source Python tooling for geospatial. So I'm Tom Kralidis. I work with the Meteorological Service of Canada, and I'm the senior geospatial architect behind our API dissemination platform, and a longtime contributor to OGC standards and open source software that implements OGC standards. So like Dave, I do have some scars from parsing XML and trying to work with XML over the years, and things have definitely evolved. So today I'll give you a bit of an overview around some of the ideas behind this GeoPython community that we have on GitHub, and some of the focus on some of the tools that are part of that community. Of course, open source is nothing. It is not new, and it's definitely not new to geospatial. I mean, we've been at it for quite some time in the open source community. We have the open source geospatial foundation, or OSGeo. Some of you may be aware of. I'll touch on OSGeo a little bit later on, and that's been in existence since 2006. So there are a number of open source geospatial tools out there. One that is near and dear to my heart, Map Server. I'm not sure if some folks in the crowd have heard of it, but it actually, yesterday was its, I think, 23rd birthday of Map Server yesterday. So it's a testament to sustainability of open source software that's being used in production systems for that long. So within geospatial and within open source, I'll take us into a bit of a dive into the corner of this GeoPython community and ecosystem that we've a number of us have been, including Dave, have been contributing to, and over the years. So I'll have a discussion, and I'll walk you through, why Python for geospatial. There are a number of languages, but we'll talk about what the some of the value proposition is for doing that. Focus on some projects. We'll talk about how that relates to standards, as well as talk about some community things, and give folks an idea of where you can go to collaborate and work with others on these projects. So why Python for geospatial? Python, I mean, I think it's the lingua franca, or it's the sort of default grammar for a lot of default programming language for a lot of geospatial environments out there. most environments do have some sort of Python support. I mean, even in a non-geospatial, non-open source world, I mean, even Esri has a deep Python support in terms of using their tools. It's relatively easy to set up. So most systems will allow you to easily set up and install Python on your operating system or on your VM or your laptop for that matter. It's quite easy to read and understand. It's very human readable from that perspective, and a lot of the way that the programming language is designed is it lends itself to very easy to sort out the logic of how to read Python code, and that's great because it lowers the barrier to contributions. So as opposed to maybe some lower level languages, which might seem a bit cryptic in comparison, Python is a higher level language, and it is interpreted for the most part, but it's easy to read and understand. Like I said, it's in a lot of places, and it's ubiquitous out there, not only in geospatial, but in a lot of different environments as well. It also has a good ecosystem of not only what's in the standard library itself. So for example, in Python, you do not need to write your own CSV parser, or you do not need to install a remote or a third-party tool to work with CSV in Python. It comes with a CSV reader, for example. The same goes with, let's say, JSON or XML, and working over the internet, sending email, a lot of tooling and a lot of functionality that maybe languages in the past have had to bolt on third-party libraries. Python has those sort of in the box already with the default installed. Now, that doesn't mean that if there's something better than what the standard library offers, that could be made available through other tooling. So the standard library is pretty, I would say, pretty rich. Also, there's a package index. So for groups, organizations that are creating Python packages or libraries of source code to do very specific things, those are, there's a platform to be able to publish those packages to, so that others can find them and install them and use them. Obviously, Python, a lot of Python projects have a heavy presence on GitHub. I mean, GitHub has all sorts of projects in different programming languages. Python is definitely one of the top ones that are there, for example. And from the perspective of lower level languages, Python sort of it goes nice with code with code that's written in C or C++. So it's relatively easy and powerful to glue Python code or to build Python libraries, sort of integrating directly with C or C++ code. So for example, if some of you have used the open source geospatial tool GDAL, which is written in C++, C/C++, there are Python bindings or hooks that you can use, and that kind of integration is relatively straightforward between those two languages. So it plays nice with anything that's in C or C++ for that matter. Fast enough. So I think for the most part, writing a C program will get you something extremely fast that works extremely fast. But so you can write a C program that is faster than a Python program, but you can probably write a Python program faster than you can a C program. And I think one of the values is in today's world, I think it's fast enough is good, in my experience at least, and it facilitates rapid development or rapid application development for that matter. So I can sit down in a day or two and write a Python program and get it to feed or meet a specific workflow, and that gets me up and running. So in the era of prototyping and coming up with things that are fast enough, but writing them quickly for a rapid turnaround and being agile, that's the word I was looking for. I would say Python is a strong candidate for allowing that to happen. So there's no shortage of Python out there in the wild in general, and in geospatial, most, if not all, geospatial environments have a heavy Python presence one way or another. So I've enumerated some projects here that are used in the Python, in the Python sphere, and I'll talk to some of them. But we can see here that over the years in the GeoPython community, we've developed a number of different tools that do a number of different things. So I'll get into some of them later on in this presentation. And the list goes on and on. So I should probably qualify and clarify and say that there is the GeoPython community as we know it on GitHub. However, there are other Python tools that exist in other communities, which are not in the GeoPython community, let's say, which we use just the same. So it's a very big ecosystem, of which the GeoPython community is one of them. So for example, Shapely exists in a different Python sort of geo community on GitHub or in the geospatial ecosystem, and that's great, as well as those other projects that you see there. So here again, I've enumerated some of the tools that are used and that have been developed. Previously, I mentioned standards. So the one thing that's been really key to Python implementations of geospatial are open standards. So I mentioned before, free and open source software and open standards. So that's it's quite a nice combination to have open source geospatial software which implements open geospatial standards, and standards from the Open Geospatial Consortium are front and center in a lot of the tools that have been built, as you can see in this in this matrix. So you'll see in this matrix, for those of you who are familiar with OGC standards, you will see some of the first generation OGC standards, which is what I call them. So things like WMS or WFS, web processing service, CSW, catalog service for the web, and so on. But you'll also see some of the evolving OGC standards with regards to APIs, such as, well, we call them OGC API in general, but that involves a new generation of web service standards and API standards from OGC, which are meant to supersede the first generation of standards. So, for example, in WMS, that's being replaced by OGC API maps. WFS, or Web Feature Service, is being replaced by OGC API features, and so on. The first generation OGC services, they will be still out there for years, and they will be in a maintenance mode and will be supported. But increasingly, we're seeing these OGC APIs come front and center. I'm not going to dive too deep into all the standards and what they're all about, but I'll just maybe give a little bit of an anecdotal here by giving an example. So in the OWS Lib project that Dave mentioned, I implemented Web Feature Service Client, which was based on XML and the first generation services. And at the same time, we implemented a couple of years ago, we implemented an OGC API Features Client, which is meant to supersede the WFS. And the OGC API Features Client was 1/3 of the code, of the lines of code. And one big reason for that is the proliferation of JSON and GeoJSON, for that matter. And that's a really big thing at the implementation level, because in the XML days, we would basically have an XML document and you would parse it into an object model, and then you would work with that XML in the space of your programming language, so in this case, Python. So in OGC API, where a lot of JSON and GeoJSON is used, in Python, that is basically a dictionary, which is already a built-in object model into the language. So it's really powerful, and it cuts out a lot of overhead and hops, if you will, to be able to work directly with those kinds of formats and those kinds of API patterns, which are a lot more RESTful, if people are aware of the term, than previous. So you can see in this matrix a lot more OGC API style standard support. So as you can see here, in the GeoPython world, We have clients such as OWF Lib or GeoHealth Check that are able to connect to these services and find things or visualize things or access or subset data. We also have servers, which, from a client server perspective, the servers obviously provide the data or provide catalogs around these things. And then we have tools around formats or encodings which allow decoding or encoding and other types of functionality. So you either have server tools, client tools, or toolkits for that matter. So we have a rich ecosystem here of things you can do with small, modular, and reusable Python packages that are meant to sort of work together. And a lot of these packages, I probably want to add that a lot of these packages came out of different projects, came out of bigger projects. So as we wrote, big Python projects in the past, or code bases, there are bits of them that, when we analyze them, we say, well, we can probably pull out this part of this package and make it a standalone thing, so people can reuse just this part and not have to download everything else into their system. And that's what a lot of this represents. So while there are all-in-one tools that let you do absolutely everything, there are a lot of small tools that allow you to be able to mix and match and take on this building block approach to writing code with open source geospatial Python tools. I'm going to walk through and maybe talk about a few of the tools, focusing on them in this presentation. One is called PyGeo API. PyGeo API is an OGC API reference implementation. It was created on 2018 on Valentine's Day. Happy to say I'm still married, but for that matter, it implements a lot of the OGC API server standards, such as OGC API features, processes, records, maps, coverages, EDR, environmental data retrieval, which some of you may be aware of. So it implements a number of these standards. We have a growing team from a number of different organizations, and it is an OSGeo project. So I mentioned the Open Source Geospatial Foundation, which is a nonprofit organization that is supportive of open source geospatial software, including Python software. So we are minted as an OSGeo project, and we are minted as an OGC reference implementation. So that's quite important, because a reference implementation allows people in the OGC context, it gives people confidence that a certain application is doing exactly what the specification says it does. So you can take confidence in that and use PyGeo API and say that your organization is deploying an OGC reference implementation and it does everything by the book. Or you can just look at the source code and study it if you're writing your own for whatever reason. So it's kind of, from a reference implementation perspective, which a lot of the GeoPython tools they are OGC reference implementations. They do allow for that kind of review or the confidence in deploying those things out in the wild. It has a relatively light installation footprint. So here I have a very simple example of installing via a Python virtual environment, if some of you are aware with that type of environment. So it's just an isolated way to set up an environment on your computer, and this in 4 or 5 minutes you can put everything together and stand up a minimal PyGeo API OGC API server with some sample data sets and get you off and running. There are more elaborate ways to install PyGeo API and use it. I mean, Docker is definitely a targeted deployment environment that we have in PyGeo API. We also have Debian or Ubuntu packages. So an important thing around these tools is the ease of installation and the ease of deployment in a lot of different environments. So we've tried to cover and be robust from a perspective of installing PyGeo API in a number of different types of environments. So there's an install there. You can get through that in 4 or 5 minutes for a minimal implementation on your computer. If you go to piezoapi.io, I mean, the website's there, and there's all sorts of links and documentation to help you out and get you started for that matter. The project itself, it's a core abstract API, so it's a very extensible suite of API tooling. So where is that valuable? That is valuable because it will let you create your own plugins. So let's say you wanted to connect to a certain type of data format, which maybe Piezo API doesn't support. Then you can write your own plugin in Python and connect it into Piezo API, or you have a very specific web API that's internal to your organization. You can write your own sort of handler in Piezo API to talk to your web API and make it, publish that as an OGC API features or coverage or metadata thing. You can. It's basically very extensible and allows for these plugins. So the basic pattern we have in Piezo API is we have a core, and which enables Python programmers to write their own plugins. Which these plugins that you can write, you don't have to contribute them back to Piezo API if you don't want to, or if they're internal or specific to something in your organization. So we allow that extensibility without touching the core per se. So the core is a relatively robust piece in the software, and then we have all these plugins, the abilities for people to write these plugins and have them be maintained in a certain way outside of the Piezo API code base as required. We support very simple configuration using YAML. For those of you who are familiar with OpenAPI, we have automated OpenAPI document generation and management, and I mentioned the deployment and the plugin framework. So I would say, well, we're over 5 years on in the project. We have a number of production installations out there with the Meteorological Service of Canada. I mean, we deploy Piezo API in production, and we get tens of millions of hits per day in a mission-critical 24/7 weather environment in terms of using Piezo API for features and coverages and processes and records for that matter. And there are a number of other installations, both in other government organizations as well as international efforts. So one effort that I'm involved in is with the UN World Meteorological Organization, and we're revolutionizing the way we do data exchange through something called the WMO Information System version 2 or WIS2, and we're using Piezo API in our reference implementations in WMO for users to publish their data through APIs and so on. And I think I probably should mention that a lot of efforts closer to home, or at least in North America, are also using Piezo API. Some of you may have heard of this GeoConnects project that some of you are involved in. It's also using Piezo API for features and for sensor things, implementations and facades for that matter. So it's getting a lot of play in the international community, and it's being used across a number of different projects. I'll end my Piezo API rant by saying that we do have, if you go to the website, you'll find all sorts of links to, we have an online workshop. So we have a diving into Piezo API workshop. We do present at a lot of conferences and meetings. There is an open source geospatial FOSS4G meeting in Kosovo in June, and we are presenting the project there. We're also giving our diving at the Piezo API workshop at that event as well. So for anybody who's attending that, feel free to come up and we can discuss Piezo API and GeoPython for that matter. So I'll stop there on the Piezo API front. Now carry on with PyCSW now. The PyCSW is a longer running project. I mean, it's been around since 2010, and it was originally scoped to provide an OGC catalog service for the web server. And it's an open source project, obviously. It's a reference implementation in OGC, and it's also an OSGeo project. since 2015. So PyCSW is only for metadata. It's not for any other OGC API style or first generation OGC WMS or WFS. It's purely a metadata catalog server implementation. We've been, again, focused on CSW for many years, but now we're focused on OGC API records, as well as I should also mention Stack API for those of you that are familiar with Stack. As well as we also implement a number of different catalog APIs, such as Open Archives Initiative protocol for metadata harvesting, SRU, which came from Library of Congress a while back, OpenSearch, and so on. So the basic approach of PyCSW is being able to manage your metadata. So it's almost like a tool to take any metadata you have, whether you have ISO metadata, maybe you have FGDC metadata, or you have diff, NASA diff, or OGC API records metadata, and it basically allows you to ingest it into a very generic repository, and it makes the metadata available through CSW and these APIs. So the scope is geospatial metadata. It also does translations on the fly, so you can query the catalog and find an ISO metadata document, and you can ask PyCSW to transform it to an OGC API records document on the fly. So it does support that workflow, and it does support harvesting and aggregation. So there is some relationship between, or maybe some overlap between PyGeo API and PyCSW. They both support OGC API records, but PyGeo API only supports a very simple OGC API records use case where you have your records repository, your metadata repository, and you just want to expose it. PyCSW allows more of the management function, inserts, updates, deletes, transformations, harvesting, aggregation, and so on. So it's a bit more focused and scoped on pure metadata, pure geospatial metadata. That's the difference there. And we've been, again, we've been OGC compliant for quite some time with this software as well. This is also used in a number of different environments. Currently, it's getting a lot of focus and a lot of attention in the Earth observation exploitation platform activities, where it's being used as a resource catalog for cataloging, for example, remote sensing imagery for discovery. Coming off of the server for a little bit, then maybe we'll talk about some more utility style tooling. There's a project called PyGeo Meta, which we implemented here at MSC quite a long time ago. Now I'm showing my age, but we decided in 2014 that we wanted to pull this out as a standalone project. So as I mentioned previously, a lot of times when we build these big pieces of software, there's small nuggets of things that we want to be able to, that we see and we say, well, this could be valuable for a lot of people. So this is what we did with PyGeo Meta. We pulled out a very small piece of our internal project, and we decided to call it PyGeo Meta and make it available online. So it's been online since publicly online since 2015. And what it basically allows you to do is generate metadata from a configuration file. So if anybody's worked with ISO metadata or FGDC metadata or some other metadata standard, we all know that it can get relatively complex and relatively quickly. The idea with PyGeo Meta is that we would provide basically a configuration file, which we call a metadata control file, or an MCF, which is basically a YAML file. And you create a very generic metadata object of or metadata representation describing your data set, and you run PyGeo API and tell it to transform it into, PyGeo Meta, too many Py projects, and transform it into an ISO document or an OGC API records document or a stack item or something else. This is a very valuable tool from the perspective of automated workflows. So I'll give you an example of how we use this tool in MSC. We manage a lot of our open data descriptions or data set descriptions using this format, and we basically have an internal GitLab repository with these MCF files that are in our internal GitLab, and data stewards are able to log into that internal GitLab and basically update their metadata through these configurations. Very simple YAML-based configurations. And then we have tooling or pipelines that that are listening to that GitLab repository, and they're finding the updates, and then they're generating the metadata on demand and publishing them to the right places. So, for example, here in MSC, we have a requirement to publish to our national open data efforts. We also have an international commitment to publish to WMO, and those formats are sometimes different. So we have these pipelines here basically to separate the content management from the publication using this automated tooling. You can add your own metadata formats if you wish, that allows you to, again, extend the software and write your own metadata format with regards to your own requirements. So very extensible, very powerful for automated tooling or integrating it into your pipelines. So this is the idea of reading and transforming metadata from this standalone tool. And we use some of this tool, this PyGeoMeta tool, inside each of the PyGeo API and the PyCSW tools to maybe do some metadata workflows as required. And because they're all Python, obviously they can work closer together than maybe Python code and Java code. But I'm sure there's, in Java, there's ecosystems for Java folks to do things within their own packages or projects. So this is one example of how we do things in the GeoPython ecosystem to be able to mix and match these tools. A couple of plugs. Again, we do have a workshop, the Doing Geospatial in Python workshop. This is in addition to the diving into PyGeo API workshop. So this workshop here is for all things that I mentioned and more. It's a 4-hour workshop that we typically run at the FOSS4G conferences. So we're doing that again this year in June at the FOSS4G Global Conference. And we run it it runs through via a number of interactive Jupyter notebooks. So there's some links there, and you can check that out, and it walks you through how to use all these tools with regards to doing projections or parsing feature data or working with coverages and so on and so forth. So it kind of runs the entire life cycle of geospatial using Python tools. Some links here. So this is sort of the GitHub organization. We also have a Gitter channel. A lot of our packages are put out onto Docker. And again, there's our Doing Geospatial in Python workshop. One tool that I just want to give a quick plug to is OWSLib, since Dave mentioned it at the beginning. That's basically our client that allows you to parse anything in Python, any OGC thing in Python, whether it's a content model or an API or a web service. And that's been a long-running tool that was pulled out of another bigger project by Sean Gillies, if some of you are familiar with Sean, who is the creator of the Rasterio Python package, as well as the Fiona Python package, which are both very valuable Python tools. So OWSLib sort of stands on those shoulders and Sean's creation. So again, another tool that we're able to put into our toolbox to work with geospatial in Python. And with that, I'll stop. I hope I gave a valuable overview of what our little corner of geospatial Python is all about, and some of the major projects that are involved in this community. And we are totally open, obviously, to new projects, new participants, new contributors, and helping build out this community to provide open source geospatial software in Python, which supports open OGC services and beyond. So I'll stop there. I'll take a breath, and I want to thank everybody for their time and interest, and I'm happy to have a discussion around any questions or any discussions.
Perfect. Thank you, Tom. There's a lot. It's a good coverage. So I've captured some high points and some of the links that people are dropping in the chat. And I guess I'll open the floor to folks in a second, but I wonder if you can take a second to comment on, so you mentioned the quick install and the topic of GDAL bindings. I wonder if you can talk for a second about the kind of ecosystem of dependencies and the portability of those dependencies and how that's evolved. And I guess what's your perspective on that? Like base Python geospatial capabilities versus depending on other community implementations, maybe in C, C++ like GDAL. Are there other things like netcdfc or HDF in the mix that we need to be aware of? Like, what's your take on that right now?
Yeah, it's I'm glad you brought that up, Dave. But one perspective is, for example, when we started PyGeo API, one of the goals was to have an API server that does not use GDAL. And we're able to accomplish that. And like the first major PyGeo API implementation was a basic OGC API server implementation, talk to Elasticsearch, which has nothing to do with GDAL or Proj or GEOS or any of that classic tooling. Now, having said that, a lot of open source geospatial tools, as well as commercial geospatial tools, are using those packages underneath the GDAL, Proj, and maybe GEOS. I mean, GDAL is for the format translation, Proj is for doing coordinate reference system things, and then GEOS is maybe doing advanced geometry processing. Excuse me. Those are based on C or C++. In the Python world, there's been a number of projects which implement bindings on top of those. So, for example, on top of GDAL, like I mentioned, we have raster.io and Fiona. On top of which are Python. On top of Proj, we have PyProj. On top of GEOS, we have something called Shapely. And to install those high-level Python tools, they need to have the libraries from those C packages underneath. So there is a bit of a dependency chain. It is a little easier with this idea of Python wheels if folks are familiar with those, which are basically pre-compiled installations for a given architecture. But things are flexible enough for, I would say, you to be able to to make your own recipe to come up with your system. I mean, Dave mentioned netcdf. We do have installations of PyGeo API that install the netcdf Python libraries for example, which need the netcdf C libraries, if I recall. So it's definitely modular and allows you to mix and match accordingly. But for the 5-minute install, I mean, that basically installs PyGeo API with everything, with nothing more than the standard library for the most part. So, for example, if you want to publish a CSV file as an OGC service, you can do that without downloading the rest of a whole dependency chain of tooling.
Cool, thanks. Yeah, it's an interesting evolution from the R spatial world. I think a lot of the same rules apply, and it seems Proj in particular, I think, is the one that is kind of the slippery slope dependency. Once you've got Proj, well, why not bring in GDAL, right?
Yeah.
And anyways, it's interesting. So I'll open the floor, see if others have questions, and also if you just want to kind of share takeaways. I want to make sure we're recording lessons learned here, what you're hearing. Anybody online, go ahead. Oh, come on.
Are there any other tools in the Python space that folks are familiar with and have questions on, which maybe weren't discussed so far?
Oh, I see Thomas Martin just came on. Do you have a question?
Yeah, I have a quick question. And again, I'm not familiar with the R world at all? Maybe some people on this call are. I know a lot of people use R for geospatial type workflows. This is more of a general question. Is there any holes in the Python ecosystem that R can fill, or vice versa? I'm just more curious if you're really geospatially focused. Can you do everything in Python that people can do in R, or is there still a big hole that R can do that Python can't?
That's a good question. I'm not very versed in R, although I would say that in the geospatial Python world, we have pretty good coverage of things that you can do. There's also tools like pandas, and that has GeoPandas for that matter. There's Xarray, and all the tools that are coming out of that community. I would say it's a relatively good coverage. I know R does some deeper statistical things. I'm not going to pretend that I know very much about R. Obviously, Dave and others can comment better there on the differences between. But I think we have pretty good coverage in the geospatial world so far, with regards to the tooling and what you need to do with it.
Yeah, and it's I mean, I run a project where basically all of our software development is in Python, but I'm an R developer, and I'm seeking out parity between the two. And there's a place and a purpose for both at the end of the day. So anyway, so we have actually a question to kind of follow up on the dependency thing. You mentioned GDAL, and kind of avoiding it, or trying to have no GDAL dependencies, but then it ends up creeping in because it's required for some of the plugins, basically. And I guess what do you see in somebody somebody dropped a tweet about GDAL not working with Python wheels, because it's bigger, and then Conda came into the conversation. And I guess what's your crystal ball say with GDAL and Conda in the mix going forward?
Yeah, I mean, it depends on your environment. GDAL's role, I mean, GDAL has its own Python library, or its own Python bindings for that matter. But there's also Rasterio and Fiona, which are more Pythonic, and it doesn't look like you're writing C++ in Python with Rasterio and Fiona. So it sort of makes it a bit more of an easier entry for the Python developer. So I think all those will continue to exist, both the native GDAL libraries, as well as the ones that are the value-added ones that are on top. I don't have too much to say about Conda, because a lot of the deployments that I work on are based on Ubuntu and Debian, and we do not use Conda period for anything like that, because of the stability that we need, that we get from Debian packages and Ubuntu packages. But I imagine that GDAL continues to live on Conda, and it will, and there's a lot of valid use cases for using a Conda environment. But I may be a bit more biased because of the mission critical hat that I wear. But from an R&D perspective, sure.
Yeah, that's a really interesting dichotomy. Our team uses Docker builds in production that once the Docker image is there, it's fine. So if the build fails, it's not really the end of the world, I guess, to get around some of that kind of production dependency issue. But there is a real divide between kind of scientific Python and production web app Python, and those two worlds kind of meet here, which it's interesting.
Yeah, no, that's definitely a good point. I mean, even for us, using Docker is a discussion, because who maintains the OS that's underneath that Docker image, security, there's so many moving parts with regards to that, and who does the actual ops, and there's a gray area there. But but there's a way to deploy those things for operational as well as for R&D. Both are valid, and all of them are needed.
Yeah, and a strength of the approach you guys are taking in the GeoPython world to have a minimal dependency core that you can install regardless of all that. I think that is really a strength of the approach.
Yes, and I would say, now that you mentioned that, Dave, I would add to that as a maintainer of a lot of these projects that have been around, for many years, I'm pretty careful and cautious on what's introduced dependency wise. So there's a trade-off from a long-term sustainability perspective where there might be a very attractive new way of doing things, and this library can do absolutely anything, and I'm going to include this. So you have to offset that from where I balance that against what's the long-term sustainability. And one thing I always do is I say to myself, well, can this work in a virtual environment, which I understand is a very basic, and I know it's a very basic way of implementing a Python environment. But if you can run software on something as simple and crude as a virtual env, that gives you functionality, I mean, that software is going to live quite a long time, which is what we see here. So I kind of have that hat on when I do review things. So I say, okay, what's the absolute most simple way? How can users get up as soon as possible? And I always like having the 4-minute install, the 5-minute install, as well as installing into a very a very simple environment. I mean, I was doing just to add to that, for an example, I was doing with a small footprint. I was doing training somewhere in Africa a couple of weeks ago, and downloading it was a challenge. The bandwidth was a challenge. So having these really small packages, really small footprints, it goes far, and it helps with the modular approach and long-term sustainability. I mean, OWS, for example, has been around since 2006, and it's had very very low barrier dependencies, and it continues to it continues to work, and it continues to be in a lot of Python based software. So and that's because of the good work that especially a lot of the packagers are doing. And I think one of them is actually on this call from a Conda perspective. So I do appreciate and happy about that. But there's something to be said when you develop software and you do imports. You balance the functionality with the long-term sustainability, and you look at what you're importing, and you say, okay, well, how long has this library been around, and who's maintaining it, and how active is it? What is the pulse of this project? And that plays a role into depending on what your goals are for building out your tools.
So many trade-offs. All right, any other questions, folks? We got another 10 minutes if folks want to take things in a different direction.
Hey, Tom. I got a question for you about catalog stuff. We used to be use PyCSW, do CSW stuff all the time, and I use and then sort of Stack came along and started getting a lot more traction than, at least in our community, than the CSW did. So I was really interested in your talking about sort of how Stack is sort of part of PyCSW, I guess. And so how would is there a way to interact between say PyCS, if there's a bunch of stuff in PyCSW that's been harvested ISO metadata, and that and now you're querying that, and now you have some Stack catalog that's got different assets. Is there some way to search both of those in some way, or I'm trying to say?
Yeah, I hear you, Rich, for sure. Good to see you again. I miss our long-winded conversations around catalogs and metadata, and I'm looking forward to having more of them. Stack. So if, for example, in PyCSW, which does what you just mentioned, we support the Stack API. So if you have a repository of ISO metadata, then you would use PyCSW stack endpoint, which basically would let you search, and then you would get stack items back. And it would take the ISO document on the search and then transform it into a stack item on the fly. So from a tooling perspective, PyCSW does that. PyGeoMeta does the exact same thing. I mean, we can go from an ISO to a stack. We can go from a stack to an ISO, and so on and so forth. Higher level stack, the content models around stack are typically around Earth observation, and in OGC API records, as Dave has put in the chat, we're trying to create a metadata model for all different types of resources, whether they're EO or not, or whether we might have metadata for a service or metadata for a process, metadata for some sort of execution, which is becoming increasingly, increasingly popular. So one way, from a standards perspective, that we're looking at implementing both of these, I would say, from our work in with the World Meteorological Organization, where the OGC API records is basically the catalog for the collections, the high-level collections. So this is my data set collection. And then we have stack for the granules, where if you're looking for a specific scene, or if you're looking for a specific weather variable, weather field from a model run, for example. So we have records for the collection level metadata, that's the word I was looking for. And then we implement stack for the granules, if you will, or the item level metadata. So that's a pattern. People can implement things the way they want, and granularity is all the way across the, there's a lot of different opinions on granularity. So it's really important, from a community perspective, to get those things straight. And there's communities who just do stack, and there's communities who just do OGC API. I like to use both because for the reasons I just mentioned around the different levels of granularity and how you want to how you want to search things. And that also becomes really important for harvesting and aggregation. So maybe we start harvesting collection level metadata, because harvesting stack items is might get expensive when you have large repositories. I mean, we do 52 terabytes a day of data here at MSC. So do we want to be doing harvesting of all the stack items that we generate? Might be expensive, but we can definitely harvest the collection level metadata that can point it to stack APIs or static stack catalogs from that collection level metadata. Just as an example.
Yeah, interesting. So you could convert you could just basically export like data that had been ingested as ISO into PyCSW. You could export it as like stack if you wanted to.
Correct. Yeah,
Okay.
It's exactly what we're doing with some of the Earth observation projects that I've seen in Europe. They're taking basically catalogs of Sentinel, Sentinel imagery. Some of them have come with their own ISO documents, and ESA has their own XML. We create an ISO document, stuff it in PyCSW, and then you can hit PyCSW and ask it for a CSW or an OGC API records or a stack API, and it does, as you know, Rich, it does all that transformation on the fly.
Yeah, cool. All right, thanks, Tom.
Yeah.
Excellent. I think we probably have time for one more topic or question. If nobody else has one more thing, one thing I don't think we've touched on much here that I think is worth drawing out a little bit or calling out. You've got geo health check and geo usage as two things there. Can you talk a little bit about, I'm assuming that's monitoring and log analytics?
Yeah, good question. Geo health check is basically monitoring. So you can set up monitors to ping your WMS every 5 minutes, or ping your OGC API feature server every every 3 hours and get a health check report saying, it's working, or it's up, it's down, or it's not behaving the way it should. So Geo Health Check is basically the quality of service monitor plus for geospatial. So not only will it tell you that your WMS is up, but it will tell you that it will evaluate for you whether your WMS is behaving like a WMS, and it does specific checks based on the given standard. So it'll do a get capabilities, it'll do a get map, make sure it, all those things are working coordinated. So it's a value-added quality of service monitor. Geo usage itself is basically for logs. It was basically built to scrape web logs that are based on OGC services. So, and it does things like scrape this web log, what the most popular layers were in this day that were queried from this, that were asked for from this WMS, or what is the most common projection used, what is the most common B-box used, and so on. So again, it's metrics analysis with a value add for geospatial in terms of analyzing OGC services, because it knows the patterns that we use in OGC services to be able to do analytics on them, for example.
Cool. Yeah, no, those are, I think that really highlights, that, not the distinction, but it highlights that a large part of the target here is enterprise app support, right? And having that kind of infrastructure is super important. That's really, anyways, it's part of the puzzle that I think people tend to not realize is even there many times. And it's like, oh no, you really do have to have that stuff.
Yeah.
Anyways,
Part of
okay.
the chain.
Thank you so much for the talk. This is really, really interesting. I'm super stoked that so many people came along for the ride. Next month, we have something entirely different. Many of you probably saw Waldo Jackwith, who was with 18F, is going to be giving a rant and rave with a somewhat heavy title. Software procurement has failed us completely. And I asked him to add, but no more. So I'm really looking forward to that one. It should be interesting. I hope everybody comes along for the ride. It should be more about federal IT procurement and how we evolve IT in the federal sphere, and should be pretty eye-opening and give people a sense for some of the factors at play here for IT interoperability when it comes to kind of big data providers, infrastructure and such. So that's coming up next month. I captured some takeaways here. If others have takeaways, send them over in Slack or send them over in email. I'll be happy to plow them into the record of this talk. This was recorded. It'll be on YouTube, and we'll keep everybody connected. So thank you very much and have a good afternoon.
Thank you.
Cool. See you, everybody.
Thank you, Tom.
Thanks. Take care.